together by taking a paintbrush and moving pollen from one flower to another. And then months later, these pea pods develop, and they got peas inside of them. Peas are seeds. And he plants the seeds in the ground. Okay? He plants the seeds in the ground, and up come the baby pea plants a few days later, and then he can look at their traits. So he can mate two pea plants together and look at what their kids look like. And by doing this, Mendel figured out how genetics works. He was the first guy to do it. And he's kind of famous for that. And I'm going to show you his experiments. Here it shows what a pea flower looks like. And there's his little paintbrush right there. And there are the pods, the seeds that develop. And so, let me show you his experiment. Now, he did a number of experiments. This is probably the simplest one. He took pea plants that were tall. And so, I'll represent that. This is the ground here. I'll represent a tall pea plant with a green line. And he mated them with pea plants that were short. And I'll represent that with a short line. Now, he called these parent plants the pea generation. Pea means parent. And when he mates two of them together, he says that he crosses them with one another.
So what is it?
Now, hold on. These plants were true breeding because he would mate them with themselves generation after generation. You can actually mate a pea plant with itself. They can self-fertilize. And generation after generation, these turned out tall and these turned out short. So he said these are true breeding pea plants. And then he made it a tall one with a short one.
Did you do it both ways or just one way?
He did it both ways. Across the short with the tall and across the tall with the short. Now, at the time, the theory of inheritance was called blending theory. That the kids would be a blend of the two parents. So if blending theory held correct, if you made it a tall with a short, what do you think you'd get?
Medium.
Well, he didn't get that. He said the next generation he called the F1 generation, which stands for first filial generation, because filial in Latin means kids or sons. You're a Latin scholar?
Mm-hmm.
Very good. So he didn't get medium plants. You know what he got? He got all tall plants. So Mendel has already disproved blending theory with that simple experiment. It's not blending theory.
Burn them at the stake.
It's not in pea plants. So, what is it? Well, what Mendel then did was he crossed two of these F1 plants with one another to see what he'd get in this next generation. The next generation he called F2. You know what he got?
Short and tall.
He got, you're right, Isaac, he got short and tall.
Nailed it.
But he got them in a specific ratio.
3 to 1.
He got them in a 3-to-1 ratio. 3 tall to 1 short. Now, he didn't just grow 4 plants. He grew about 1,000. And he got about 750 tall to about 250 short, which is a 3-to-1 ratio. Now, Mendel's a smart guy. He knows a lot about math. He knows about statistics. And he's seen a 3-to-1 ratio before. And y'all have too. Let's say I have 2 coins. What's the chance if I flip one coin of it getting heads?
50-50.
50-50. It was heads that time. Flip it again. See if I get tails. I did. I got tails. 50-50. What's the chances if I flip 2 coins of getting 2 heads?
50-50.
1 and 4, right? It's still.
It's 25%.
Ah.
It's not 50-50, it's 25%. Which is exactly what this short one is, 25%.
Why is it?
It's 25 because it's 50-50 for one coin, and it's 50-50 for the other coin, so it's 1/2 for each. But you have to multiply those fractions together to get the chance for both coins to be heads.
So it's like 1 times 1, so 25.
1/2 times 1/2 is 1/4, 25%. You'll learn this stuff if you ever take a statistics class. But Mendel, he was a math teacher, so he knows this stuff, right? So he sees the 1/4, and from that he figures out that genetics must be working like 2 coins somehow. And he comes up with the modern theory of genetics, which is this. Mendel figured out there were 2, well, he called them alleles. Today we call them genes. But that each individual plant had 2 alleles, like 2 coins. And he said that the tall plant has 2 tall alleles, and we'll call those big T, big T. And that the short plant has 2 short alleles, and we'll call those little t, little t. And that whenever you mate plants together, when you cross these 2, that each plant only gives one of their 2 alleles to their kid.
Because it's separating.
Because they separate in meiosis. But Mendel didn't know anything about meiosis because he didn't do microscopic work. But about that time, some other people were looking under the microscope and figured out meiosis. But the alleles separate and end up in the sperm or the eggs. And you only give one of your 2 alleles to your kids. So these kids would have gotten one of the big T's from their dad and then one of the little t's from their mom. So every one of these kids should be big T, little t. So Mendel said, why does that make them tall? Well, he said big T must be dominant over little t. So he called big T, love having 2 boards. You don't have 1 board. Big T equals the dominant allele. And little t, he said, was recessive. And so when you mix big T and little t together, they're going to end up tall, not short. Because big T dominates over little t. Yes?
So are you saying that in F2 there's a chance of 2 little t's?
Ah! Let's get to the F2. If you take 2 of these and you cross them, there's 4 possibilities. There's big T, big T. These 2 alleles can get together. It'd be like flipping a coin and getting 2 tails. You could have this big T allele with this little t allele. Big T, little t. That'd be like a tails and a heads. You could have this little t here with this big T there, which is also going to be big T, little t. Mendel chose to always put the dominant allele first if there's a combination between the 2.
So it doesn't really matter?
Doesn't really matter. If there's a big T and a little t together in an organism, it's going to be tall. And so Mendel chose to write the big T first if there's 2 together. What's that? Like foiling?
Yes. First, after, and last, like with math.
Yeah, it's like foiling.
No clue.
And then the only other combination is this little t with that little t, which is like two heads. And there you go. Only the 2 heads on the coins gives you the short.
Will that always happen, or is it just by chance?
Well, it's just like flipping coins is chance. But if I flip 1,000 times, I'll get 2 heads about 250 times. It won't be exactly 250 because there's a random chance for each flip. But the odds will work out where it's about that.
So you can get a general area where it should be, but you can't get it exact.
Yeah, you can't exactly predict what one child's going to be, but over enough children, you can guess it'll probably be about 250 out of 1,000. Yeah.
So this is awfully simple. Does it get more complex?
It gets more complex.
Okay.
This is called simple Mendelian genetics. It's actually called that.
Oh.
Simple Mendelian.
Simple. Okay.
And that's it.
Oh, that's it.
Mendel did this experiment, and he wrote it up in his little logbook. He had a logbook just like you guys have. And he wrote it up in there, and he was right. This is how it works. And he wrote it up, and he showed a few people, and then he died. He never became famous in his lifetime. And like 40 years later, in other parts of Europe, they're trying to figure out how genetics works, the scientists of the day. And somebody showed them Mendel's work, and they go, he already figured this out 40 years ago. And so Mendel's kind of famous for that. And so they named this whole idea of dominant and recessive is called Mendelian genetics. Huh? What do you think about that? Now, there's some words you need to know. If two alleles are the same, Mendel called them homozygous. Homo means the same. A homosexual likes the same sex. Yeah, I knew you were thinking it. I just had to say it. This is homozygous dominant. This is homozygous what? Recessive. Now he called them, if the two are different, if this allele and that allele are different, he didn't call it homozygous, he called it heterozygous. So this is the heterozygous. Now, he also had a word the word that means, if you're referring to the two alleles, like when I say big T, or big T, little t, I'm talking about the genotype. The genotype is the letters, the alleles. There's another word he used called phenotype. The phenotype is a description of the organism. So what would the phenotype be for this?
Height.
It'd be tall.
Tall. Okay.
A description of what the organism looks like is the phenotype. That's a tall plant.
So did he never get like a medium plant?
Never got mediums in these. Now we'll see there is a way to get mediums. We'll talk about that later. Not for these pea plants though. Pea plants are either tall or short. There are no mediums. That's what got him thinking blending theory is wrong in the first place. Because he only saw tall and short pea plants. He never saw any mediums. And he's like, after blending theory, let's see what happens when we made a tall and a short. Let's see if we get any mediums. And sure enough, he didn't. So he had read up on blending theory and said, wait a second. He knew a lot about pea plants. He said, wait a second. I don't think that's right. He's a smart guy.
You nailed it.
Here was all the experiments he did. Well, not all of them, but this is a lot of the experiments he did. Look, he found out tall was dominant over short, and there was his results. 787 tall to 277 short. He found that inflated pods were dominant over constricted pods in a 3-to-1 ratio, 882 to 299. He found that round seeds were dominant over wrinkled seeds, 5,474 to 1,850. A lot of P's. He found that yellow were dominant over green, 6,000 to 2,000. He found that axial flowers were dominant over terminal flowers, 651 to 207. He found that purple were dominant over white, 705 to 224, purple flowers. And he found green pods were dominant over yellow pods. All of them in about a 3-to-1 ratio. It's not going to end up exactly 3-to-1 because there's randomness in it. Like tossing coins. If I toss a coin 4 times, I'm not going to always end up with 2 heads and 2 tails. Sometimes I might get lucky and get 4 straight heads. But over thousands of flips, it'll kind of end up close. So Mendel did a lot of experimental work here, and the monks had a lot of pea soup. I use that joke every year. I don't know. They might taste the same.
That'd be another phenotype, right? Taste.
That's right. Taste is phenotype. Sweet, sour. Now, a guy came along. His name was Punnett. Reginald Punnett. And Reginald Punnett said, hey, this foil thing is hard to understand. I get confused doing the foil thing, Punnett said. Punnett said, what I'll do is I'll make it a little easier. I'll make a square, which he called a Punnett Square.
Oh, I remember this.
Remember these?
Yeah.
Do you know where it talks about Punnett, the man in the book?
I don't know.
I think they left him out.
Wait, is his name in
Oh,
here?
yeah.
They didn't talk about Punnett Square?
Where is that?
Yeah.
It's later on.
Yeah, like
You skipped
They have them on.
Yeah, it's back here.
I skipped?
198. It's like, oh,
We hadn't gotten there yet.
they don't mention Punnett actually.
What? A book doesn't mention what?
Oh no, Punnett Square is page 200, figure.
Punnett Square is on 195. That graph is on 195.
Yeah.
What is up there is on 195, but
Wait, 195, but it doesn't.
it doesn't talk about.
Hey, everybody calm down. It's going to be okay. I'll tell you about Punnett. She was my boy. Punnett said, let's make a square. We'll take, if we're mating 2 of these, we'll take the alleles of one parent and put them on the top of the square. And we will take the alleles of the other parent and put them on the side of the square. And then we simply drag the 2 alleles to the intersection between them to the square, and we write those alleles. So this is big T, little t. And that is big T, little t. You always put the big T, the capital letter first. And that one's little t, little t. And so there you have the 3-to-1 ratio. And it makes it kind of easier to get than trying to do this foil thing that might get confusing. The size of the Punnett Square, that's where you put the gametes. These actually stand for gametes, sperms and eggs. Like these could be the sperm cells, and these could be the big egg cells. And when that sperm that has a big T fertilizes this egg that has a little t, you end up with a big T, little t kid. Remember when I did meiosis and separated out all the chromosomes? And during anaphase, they separate and move to opposite sides? That's like separating the big T, little t from the parent, separates them. So one sperm ends up with a big T, and one sperm ends up with a little t. You see what I'm saying? And if an organism was big T, well, it doesn't matter how they separate. The sperm, every sperm is going to get a big T. Or if it's little t, every sperm is going to get a little t. So let me give you a little problem to do. Want a problem? Do me a favor, make a big T, little t, cross it with a little t. And tell me the percentages of the phenotypes of the kids. And do it with a Punnett Square.
Okay. We could do that in our head, though, couldn't we?
You could probably do it in your head, but I'm going to go ahead and do it on paper because we're going to get to some you can't do in your head. Only I can do them in my head.
All right.
Write down the percentages of the phenotypes.
So 50-50.
50% tall.
Ah, where's your pen? You need to write this down.
So, one father, T, 1, 2, 2. Perfect.
Very nice. Huh? Okay. Okay. Wait, whoa. This. All right. Nice. Where's yours? Nice. Okay. Looks like most everybody got it. That's good. This was a pretty easy problem, but you might have one of these. This parent, big T, little t, crossed with this parent, little t, and most of y'all did a square that looks like this. So half of them are tall and half of them are short. That's a 50-50 ratio, or you could call it a 1-to-1 ratio. And that's what you'll see the book calling it. They won't say 50-50, they'll say 1-to-1. One of these for every one of those. Now I'm going to give you a shortcut. You didn't have to make a Punnett Square this big. Let me show you how you need to make them to save yourself time. And this will really come in handy when we start doing harder problems. Emma, are you with me? Seems to be good. You take this one can make two different sperm cells, a big T sperm cell or a little t sperm cell. So we put big T and little t. So excited, I'm spitting everywhere. Big T, little t. And then this one can only make one type of egg, little t, right? So there's no use of putting two little t's on this side of the square. On this side of the square, we only need one little t. Because the other one's just a repeat of that one. So this, your Punnett Square can actually look like this. And you still get the same result. This is an important thing to know. Because we're about to do squares that are a lot bigger. Look on page 198. Look at that square. That square has 16 boxes. If you can use a shortcut to cut off half those boxes, or even cut off 3/4 of those boxes, you ought to use it. And I'll show you these shortcuts. We want to use these shortcuts whenever possible.
What page?
198. Let me show you. You got time for this? What time's it over?
5
3
minutes.
3 minutes. We don't have time for it. But I do have time to kind of set it up for you. Mendel would sometimes consider two traits at once. What are y'all doing? Don't pack up. Still paying attention. Mendel would sometimes consider two traits at once. For instance, he can consider a plant that's tall and that has green pods. Green pods are dominant over yellow pods. Tall and green. If you cross a tall and green with a short and yellow pod, how are you going to do this problem?
8 squares.
It's going to involve a larger set of squares. And those squares can get up to 16 in size. But a single sperm cell gets one of each pair. So a sperm cell will get one of those two. It's got to be the big T. In order to get one of those two, it's got to be the big G.
So can you just do like a T, big, like a little T?
This X cell gets a little t and a little g, obviously, one of each pair. And so when you combine those, you put the two t's together, big T, little t. You put the two g's together, big G, little g. And you'll still have a tall and green plants, but they're heterozygous. Now, if you wanted to make this with another one just like it, then we've got a lot of different sperm cells that are possible and a lot of different egg cells that are possible. And that's what this square shows. And that's what we'll pick up with the next time. So, you read 11.1 and go 11.2 up to page 197.
Heterozygous means that it has both dominant and recessive.
That's correct, yes. And if you guys want to talk to me about your essay, you can do that now. I guess you can take care of that now.
Alrighty.